All right, guys. What's going on? This is a kind of makeup and review of the reinforcement learning lecture that we went through last week. There were a couple things at the end of this lecture that I didn't get to, unfortunately, in class. So I wanted to just take a moment and go over those in this little bonus lecture as well. And then I'm going to, as I said in class, offer a little bonus lecture that I've also uploaded to D2L that'll talk about the Google Mind Atari paper, and that'll use a lot of the techniques that are discussed in the reinforcement learning lecture as well. Okay, so just to recap, guys, as I mentioned in class last time, I'm just going to do a brief overview and then slow down when we get to the new stuff in just a moment. So reinforcement learning is a very exciting, burgeoning field. Lots of cool things going on. AlphaGo, reinforcement learning using to play Atari games, autonomous driving, all these kinds of things are using reinforcement learning. So it's a very deep kind of field within AI and really machine learning. And as I mentioned in lecture last week, kind of rests in an intermediate kind of domain, reinforcement learning between supervised and unsupervised learning. The key difference with reinforcement learning is that we have an agent that interacts with an environment, and that agent, in some sense, gets to choose. It has some autonomy, depending on how we program it, gets to choose the data elements that it wants training labels for, or at least reward signals for. So that makes it a little bit different than traditional supervised and unsupervised learning, as we've seen in the past. As I mentioned also in lecture, lots of cool connections with reinforcement learning in non-AI machine learning fields like psychology, neuroscience, etc. Okay, so just to walk through this again, we talked about one of the crucial kind of notions in reinforcement learning is this idea of the trade-off between exploration and exploitation. So a good reinforcement algorithm should, in principle, strike a nice balance between those two things, where, again, we explore the environment so that we learn about its mechanics and what's successful, what isn't successful. And then once we, as we explore that environment, we develop strategies and tactics, and then we want to exploit, that information as well. Okay, so we talked about that, and I connected it with simulated annealing, which we saw back in the, it was chapter 4 in the Russell Norvig text that had to do with doing optimization, local optimization, but essentially achieving a kind of exploration of the search space through simulated annealing, so that we would jump potentially from a local extreme value to hopefully like a global extreme value, and that was controlled via temperature when we talked about simulated annealing way back when. Okay, so I talked about a few examples in class, not going to go over this again, but do check those out. I also suggest that if you have some time or some inclination, check out the OpenAI Gym. Has a lot of these demos, which are really cool for reinforcement learning as well. Okay, so just to go back to the formal problem just for a moment. So again, here it is. Kind of should remind you in some sense of just the basic sort of premise of AI at large in terms of describing an agent and how it interacts. So we have some agent that interacts with an environment via some actions, and then that environment then returns a signal, which is at minimum a new state based on the actions of the agent, and possibly a reward, right? The reward could be 0, but generally speaking, the reward is going to signal the agent as to when it's doing something well. It'll get a positive reward as opposed to when it's doing something not so well, in which case it will get a negative reward. So more formally, you can describe a reinforcement learning problem, kind of the nuts and bolts of it, via a Markov decision process. So what makes things Markovian, quote unquote, or the Markov property, is that we assume that the environment, the current state and reward only depend on the previous state and action. So it's this kind of, gross oversimplification, of course, that we make, but it makes the modeling, the mathematics, the simulation, all those things much more feasible by obeying this Markov property. And when it comes to an MDP, or Markov decision process, as I said in lecture, there are these 5 components. You could call it a 5-tuple. So we have a set of states, we have a set of actions. Those set of actions might depend on which state we're currently in, a probability of the environment, moving from one state S to another state S prime, given that the agent performs action A. Again, that's what's going to obey the Markov property. And then we have a reward signal, as I mentioned before. So the reward that the agent receives when it's in state S performs action A, and it then moves to state S prime. And then last but not least, there is a discount factor, and that's denoted by gamma. It's a number between 0 and 1. It's usually very close to 1, like 0.9 or something, as I said in class. And that the discount factor is a hyperparameter that basically kind of weighs how heavily we want the agent to make a good decision, but to do it immediately as opposed to delaying, making kind of a correct decision. Okay. So there it is. There is a Markov decision process. Again, that's kind of at the foundational level of a reinforcement learning problem. One more time, we have an environment, a set of states, actions we can perform, some reward we get, and that reward is discounted, and that discount is attenuated by the gamma parameter. So there it is. There's the basis for most every reinforcement learning problem. Just to hit this point again that I went through in lecture, the fundamental goal of an agent is to maximize expected return. So I could say, okay, agent at time little t, what is your reward? What is the cumulative reward you collect from that time to some end state or some terminal state? And that would just be the sum of the consecutive rewards. And now if we render the expected discounted reward, now we would throw in the gamma parameter. And as I said before, this will again give me a penalty essentially for receiving a reward in a delayed fashion as opposed to kind of immediately. Okay, so we put it all together. That's the thing that the agent, if it learns a particularly good strategy for a problem in reinforcement learning, that's the thing that it wants to maximize. So the expected discounted reward. So there we go. Okay. So I have kind of that in a little more depth here. We talked about this in class, and maybe I'm not going to go through it again, but again, the four main components, just adding a little bit to that, the policy. So just to mention, the policy is going to define the learning agent's way of behaving at a given time. It's typically denoted pi of S comma A, if you see that in the literature, and they do notate it that way in the Russell Norvig text. So that just means it's the probability that this agent that we've trained, when it's in state S, performs action A. So that policy would be overall, if I could describe all the probabilities for all the configurations potentially and all the actions the agent could perform, that would be a complete description of the agent's policy or strategy that it's learned. Okay, so that's the thing we tune, if you will, as the agent has experience with the problem itself. Okay, so the policy, we'd like an optimal policy, a very good policy. In the end, we talked about the reward function. And then a value function, as I mentioned in the lecture last week, so there's, generally speaking, guys, two types of value functions, and I have this later in the notes as well. So we can assess the value of a particular state to an agent, and that's usually denoted V of S. Okay, so how much does the agent benefit from being in a particular state? You can imagine. A common example would be if a particular state represents 3 moves away from a checkmate, that would potentially be a valuable state for that agent. It would have a high value. On the other hand, you can describe in more detail, you could describe the values of not just states, but what are called state action pairs. These are usually referred to as Q values in reinforcement literature. So literally you write Q of S comma A. I have that later on. In lecture notes as well. And this would be more informative than just assessing the value of a state, because it tells me not only this state, but when I perform this action together, how advantageous is that particular pair. Okay, so in theory, if I had a table, again, this probably wouldn't be feasible, as I mentioned, in a really complex problem, but if I had a table where I could look up all the values of all the states for an agent, then, and if I knew these things optimally, that would inform, an optimal policy for the agent. Okay. Similarly, if I had a table where I could just look up the Q values, that is the values of all these states and action pairs for an agent, and I could assign those things optimally, that would give me an optimal policy. So for that reason, hopefully that's pretty clear to you guys, but for that reason, then reinforcement learning really boils down to oftentimes coming up with good and feasible approximations of, again, these value functions, either for the states themselves or for the state action pairs, okay? Now, as we well know, I think through this course, and if you've had some algorithm classes in the past, it's not going to be feasible to, unfortunately, just fill in a lookup table for a complex agent-based problem, because there's just too many darn states and actions, right, to sort of keep track of. So with chess and Go, that wouldn't be feasible. So we have to have some way to compress that information, and that's really kind of the art of reinforcement learning. Okay, so there's a general overview of that stuff. Value functions, again, I have some more on that a little bit later. And then this notion of a model, which, as we talked about way back in chapters 1 and 2 of the Russell Norvig text, it's nice if an agent has a model, that is, it has a way of simulating or mimicking the behavior of an environment. Oftentimes in reinforcement learning, for example, through Q-learning, it's not actually necessary. This is a huge upshot of reinforcement learning oftentimes. It's not actually often necessary that we have an explicit model of the environment. We can kind of model things implicitly via value functions. On the other hand, you could have an explicit model of the environment itself. Now, just to keep this in the sort of AI realm of things, a model, in this case of an environment, could really just be a proxy for an adversarial agent. That is like some agent or person I'm playing in chess or Go or what have you. So model is optional. Okay, if we don't have an explicit model of the environment, it's called model-free, and Q-learning for the most part is a model-free approach. But we still could have a model if we adopted a sort of a different approach to reinforcement learning. Again, one of the big benefits of reinforcement learning is it's not often the case that we need an explicit model of the environment. Okay, so there's the recap of kind of those 4 components of a reinforcement learning system. There we have it. So maybe just to kind of reiterate some of the benefits of reinforcement learning. If we look at tic-tac-toe, right? So we've talked about the Minimax algorithm, of course, in this class. So you'll recall what the Minimax algorithm looks like. So here would be just a quick snapshot from Minimax for tic-tac-toe. So if this is our current state and X has the next move, these would be like 3 optional moves it could make. It could go, you could do an X in the middle, down the left, down the center, down the left. And then we could look ahead and propagate the Minimax algorithm and say, okay, what is min going to do optimally? What is max, in this case, X, going to do? And then we can just look at the terminal states here and assess, okay, do they win, lose, or draw? So if they draw, it's a 0. If they win, it's a 1, essentially. And then we can essentially propagate those scores backward to determine, as you'll recall in the Minimax algorithm, what the best strategy is for X. So if we go back, fill in this complete essentially table of states, and now we say, okay, in hindsight, what is X's best move? Obviously, based on what we filled in here, X's best move is to go on the right. So in other words, to put an X in the lower left, and you're guaranteed to win in that case, right? So that's awesome. As we showed with Minimax, is just a classic adversarial, agent algorithm. Now, it works very well, as we talked about in class, when I can fully populate like a search tree. That would be fantastic. So in tic-tac-toe, that's feasible, of course. If not, we can apply alpha beta pruning as well, so that we don't search various paths in the search graph that are unnecessary. We could also, on top of that, use various heuristics that could cut the search short beyond that. So we could say, oh, let's just stop at depth 4. Anything beyond depth 4, we could approximate Max's value or potential for winning from there. So there's lots of ways around that. We talked about that. But some drawbacks nonetheless of Minimax is, for one, we're assuming the behavior of the opponent, right? We're assuming in particular that min is an optimal opponent, okay? So with reinforcement learning, I don't have to do that. I don't actually have to play to a specific opponent strategy in general. There are some restrictions there, but in general, I don't need an explicit or explicit assumptions about my opponent at all. So there is one huge upshot of reinforcement learning. The other thing in reinforcement learning, as I'm about to show you, is that we don't actually need to map out, right? This can be very laborious, map out this full sort of search tree, right? So we don't necessarily have to do that either. And the way we can get around that again is with value functions. Okay, so several advantages of reinforcement learning that kind of in some ways go above and beyond minimax or genetic algorithms for that matter. Other algorithms we've seen to date in this class. Okay, so the other thing I would say that's a big advantage of reinforcement learning, just to add to that, is it's actually pretty easy to pump in, which I say stochastic elements, right, or exploratory elements, right? We, as the designers of the reinforcement learning algorithm and the agent for that matter, can decide on the kind of the split between, again, exploration and exploitation. That's something that's actually quite difficult to kind of, sort of encode if you think about it in like a minimax, search algorithm. So reinforcement learning very much lends itself to exploration and exploitation. Okay. So one question, basic question remains then is that going back to reinforcement learning, if you're saying, all right, it's all for the most part kind of about how you approximate these value functions efficiently, and the better I can get with those approximations, the better kind of my agent's policy is going to be in the end. That's all true. One question remains though is how to do those updates. So I want to remind you, in a classical approach, I'm going to go back for 1 second, a classical approach to sort of agent-based search, right? If we think of day one of our AI class, searching a graph or a tree, trying to come up with some optimal strategy in this case. So to evaluate various strategies, to know when I've kind of got a good one with a classical approach like a graph search, what I have to do, unfortunately, is train a model, come up with a strategy, and then simulate various games, let's say in this case, against opponents and see how well it does, right? I have to train it, freeze the model, perform a bunch of simulations, and only then post facto can I assess, whether or not the agent is successful. Okay. Now, if it's not, and I want to retrain it, say it doesn't do that well against agents, I've got to retrain it again, run a bunch of simulations, fix the model, and rinse and repeat basically this process maybe many, many times. So with reinforcement learning, you don't have to do that. So in general, so what I mean by that is I can actually update, in this case, the values, the value functions themselves in what's called an online fashion versus an offline fashion. So in other words, I can evaluate the state functions as I'm playing a game, as I'm simulating them. So I don't have to freeze the model, do a bunch of simulations, go back, change those, weights or whatever, do a bunch more simulations, and again, get in this kind of very, very lengthy cycle of assessing how good my agent is. With reinforcement learning, I can kind of interleave all those steps or sort of boil them down into one. Okay, so what do I mean by that? What do I mean by that is just if we glance at like this is a classic equation in reinforcement learning. Technically, it's called temporal difference. And there are lots of different sort of update rules in temporal difference. It's kind of a big rubric within reinforcement learning. But just to see a basic example, how could I update the values of my states online, again, as the agent is actually playing or doing a simulation? Well, the way you could do that is you could just use an iterative update formula, and I have one. This should remind us, if you've had a little bit of machine learning or seen some of these classic algorithms, this should remind you maybe of a little bit of like the perceptron learning update algorithm for the weights, or even a neural network. It's not that different, in fact. So this says basically we would take the value of the state of S, the current value, okay, it's an approximation for the value of that state, and how would we update it? Well, we would just take the previous state value and add to that alpha, which is some hyperparameter that we can sort of tune, usually it's relatively small, times the difference between the value of S prime, the next state I encounter, minus the value of the current state. So what this means, this is all diagrammed on the right, and I encourage you to look at this in more detail if you'd like. What this is basically saying in a nutshell is I can do an iterative update of the value of the current state by peeking ahead to the value of the next state, taking the difference of those two, squeezing it by alpha or scaling it by alpha, and then adding that difference, that scale difference, to the value of the current state. What that's going to do essentially is it's going to correlate the value of the next state with the current state, right? Because if I'm in a currently a valuable state, well, then the next one is also, you know, somewhat valuable as well, depending on sort of which action I choose to get to that next state. And this is what it's going to do in the end. This is going to bring the value of the state S closer in some sense to its true value, or by correlating that value with the value of the next state. Okay, and I would do this many, many times for many states over many iterations of self-play or simulation against an opponent. The bottom line, two comments I want to make here just to reiterate that. The bottom line is this. With reinforcement learning, it's relatively easy and natural, for that matter, to update the parameters of the agent as it's playing, right? So at no point did I have to freeze, again, the algorithm, the weights, or the policy or whatever, and then simulate it and then go back and change things, right? I can do this in an online fashion, okay? And so that's the first comment I want to make. And then the second comment is, this is, you know, an evaluation that I can do with the kind of one-step look ahead, right? So this is going to correlate lots and lots of states together. And if I have a good state and the state after it is also good potentially, I want to correlate those values, and I'm going to geometrically move those values closer to one another. That is all that this update formula does. Pretty simple, okay? And so how do we get these, you know, values, these approximate values of the states themselves? We do it through simulation, through play, or through self-play in reinforcement learning. That's how it's done, through samples. Okay? So there's a basic formula there, and that's, again, known as temporal difference. Okay. All right, guys. So I talked about N-armed bandits. I'm going to pass over that, but I did talk about that in lecture. That's, again, a classic trope to describe exploration versus exploitation. It has a lot of theoretical and conceptual importance in agent-based searches, and in particular in reinforcement learning. So I talked about taking a sample average of rewards. That would be one way I could evaluate or approximate these Q values and so on. I'm going to move on past that. And I also talked about doing it in an epsilon greedy fashion actually gets you better results. That shouldn't be a big surprise. Based on, I think, what you've seen in this course previously. So I'm just going to move ahead here. And there's basically a nice iterative formula so you can update these guys. And that's basically not too different than temporal difference, a slightly different way to do it than what I just showed you. But there we go. So let's go then to the Markov decision process. So I want to show you actually how simple. I know there's a lot, you know, in reinforcement learning. There's a lot going on. But I want to show you actually how simple it actually is to train a reinforcement learning agent, just kind of in principle. Obviously, the more complex the problem, the harder it gets. But I just want to show you how these update formulas are actually very, very simple. So if we go back to Markov decision processes, remember this is the general framework for describing reinforcement learning agent, where we assume the environment obeys the Markov property. That is, to know anything about the current state, I only need to look one step back, and that tells me everything about the environment there. Now, again, a policy is usually denoted with a pi. There we go. So it's technically speaking, it's a function from states to actions, and it's going to specify what action an agent should take in a particular state. And we can describe this probabilistically if we have like a non-deterministic agent, for instance. And the objective, again, is to find what's the best policy possible. So that's a policy, we'll denote it, as is commonly done in literature, with pi star. So this would be the policy that maximizes cumulative discount, or discounted reward. Okay. So as I said before, like formally, I think I wrote this actually on the board last week. Formally, then, the optimal policy would be the policy that, again, maximizes expectation for discounted reward. And this is, again, just to remind you guys, we have to denote this with an expected value because there are uncertain quantities kind of in the mix, right? The environment could be stochastic, the reward could be stochastic, lots of different things. The policy itself could be stochastic. So having said all that, we need to take an expected value, but this is just saying, what's the, average discounted reward you're going to get? And if I can maximize that, that would be an optimal policy. And this, just down below, don't sweat over this, but this is just saying the initial state comes from some probability distribution over initial states. In chess, there would just be one initial state, right? And an action, the environment itself can be stochastic. Sorry. So this is the action with respect to this policy when we're in the state. That can be stochastic. And the next state for the environment, right, can also be stochastic. So there we go. As I said before, the goal in reinforcement learning is to come up with some both efficient and good approximations for value states. So if we take the notation one step further here, we're just going to say the value of the state S with respect to policy pi. So that's what's meant by the superscript pi there, is going to be what? It's just simply going to be the expected discounted reward with respect to policy pi and state S. So that means if I start in state S as my initial state and I follow policy pi, what is the expected discounted reward that I'll receive? And that is V of S with respect to policy pi. Okay, awesome. So maybe I won't go into this a whole lot. There are, as we've seen, guys, in the AI class, lots and lots of kind of historically classic examples that develop in parallel, with different domains and algorithms within AI. So we've seen like the Wumpus world. I showed you that, albeit very briefly, kind of last week. And we've seen a lot of problems with constraint satisfaction, map coloring, all these kinds of things, right? Minimax, classic stuff. So Grid World is yet another kind of classic example. It's a micro world, if you will. So it's a very sort of simple environment. And this is oftentimes like a proving ground, just like the MNIST data set's a proving ground for a neural network. This is Grid World's kind of a proving ground for different reinforcement learning based algorithms. Oftentimes, it's not the only game in town, but it's a nice thing to just kind of run a reinforcement learning algorithm on and see how it does. I believe, if I'm not mistaken, the OpenAI Gym definitely has, I think, a couple Grid World-like examples that you can check out in more detail as well. So all this is showing, maybe I won't go through the whole thing, but Grid World, in principle, is just this. It's a grid world, literally, okay? And it's kind of like the Wumpus world in some sense. And usually there's like a goal state, and you might have a couple states where like the agent dies or receives a penalty, if it like falls into a pit or whatever. And basically in this case, this is a very simple one. I think in this state, in this grid world, the agent starts in the upper left and wants to get to the bottom right. And then it just, it gets however many points, 10 points or 1 point when it gets to that state. And then I think, again, there's many variations of grid world, but usually there is, penalty for how long you take. So it's a discounted reward. So we don't want to just move, meander around randomly and then 100 steps later get to the goal state. So there is some urgency to get there as fast as possible. And then usually there's some basic things like if I try to run into a wall, I get, some sort of negative reward. Okay. So having said all that, you could start off with, if I wanted to train, in principle, if I wanted to train an agent to do well in this very simple grid world example, I could start off with a random policy and then approximate values for the various states it could be in. These are the number of iterations starting in a random policy, okay? And assuming we can go up, down, left, right, and again, if you hit a wall, you get like a penalty or something. So this is showing after one iteration, 2, 3, 10, and in the limit to infinity of the number of steps as well. So what are the values here? So there's no value that gets assigned basically for the initial state. And after, if we just look at this a couple steps, what's happening is the values are I guess these are all kind of negative, but the smaller negative values, I guess, are closer to kind of the terminal states there. The point really in this diagram is two things, I guess. You can approximate the value states, as we said, and they give you these numerical scores. And then also, though, you can come up with basically a policy based on those value states, right? So if you look over here, let's just jump to the very end. We come up with a kind of optimal policy after 10 states or beyond of training. And what this is showing is, I might be wrong. Sorry about this one. I think you could start out anywhere, but I think you're supposed to either get to the upper left or the upper right. Sorry. Usually there's a start and a finish, but I think in this one, that makes the most sense where you're trying to get to either state. Sorry about that. And so what this shows you, if you just glance at this, so if I start here, maybe it's a random start, like the best thing to do would be to just walk left and then I've hit the goal state, right? Or if I start here, the best thing to do would be to walk left or to go down and I, get as fast as, so it's efficient, as fast as possible, get to the goal states. Okay, so you can imagine adding complexities to these grid world examples, or it's like partially observable, or there's pits or, horrible things that can happen to the agent, whatever. And again, point being, if I approximate through experience, through self-play, even using just this, sorry to go back, but even just using this update formula that I showed you way back when right here, starting at random initial values, I could, through play, right, come up with, a decent approximation to those value states, and that would give me a policy potentially. Okay. So that was for the value states. Let's move on then to the Q values, which is another type of value function used in reinforcement learning. Now this is assessing the value of a state and an action as a coupled together with respect to a policy pi. So in plain English, what is this? This is the expected discounted reward when I start in state S and perform action A and thereafter follow policy pi, okay? So in a sense, it's quantifying. If I did this through lots and lots of, again, experiences or plays, this would quantify the value of that state action pair for me. And then from there, I could devise a policy. Okay, cool. Now, I'm going to skip, as I mentioned in lecture, some of the more mathematical details that kind of underpin the big punchline in reinforcement learning when it comes to Q learning, which is a classic approach. So I'm going to show you the kind of end result of that, and I'll explain it as well. In the advanced machine learning class, we tend to go over this in a little more detail when we talk about reinforcement learning. If anyone wants to see those details, I'm happy to talk about them. But just to give you a broad overview here. So what we would like in terms of these Q values is we would like the Q values, for an optimal policy, of course, right? So that's denoted here Q star. So this would be, of all policies possible, the maximum policy, the policy that would maximize my expected discounted reward, right? When I start in state S, perform action A, and thereafter follow policy pi. Okay, so the optimal policy satisfies what's called the Bellman equation. More properly, it's actually a system of equations, so the Bellman equations, and that's what I have in the red box here. It's not hard to show this if you basically just use a kind of clever way of writing Q values, one in terms of the other. You can use this kind of inherent iterative sort of, or I should say recurrent relationship. From there, you can actually derive these Bellman equations. It's not an esoteric thing. It's actually not that hard to show, but let's just use the result here. So there's the Bellman equations, plural. I say equations plural because this would be an equation for all possible states and actions, okay? So if I could solve all those equations, and when I say the equations again, the system of Bellman equations, I would have an optimal policy. We'd be done. Okay, so again, the problem with that is this would be a huge system. I probably couldn't even store it in memory. But nonetheless, the Bellman equations provide a very nice theoretical foundation for reinforcement learning. They also tend to come up in dynamic programming if people have had experience with that too. Okay, so what is this? Let's just look at this for a second. So the Bellman equation says this: the Q value for the state action pair in the optimal sense, for the optimal policy, would be the expected, again, discounted reward of the immediate reward. That's what this R signifies. The immediate reward I get for when I'm in state S performing action A, okay, plus gamma, the discount of the maximal action for the next state. So think of this, the Bellman equation, it's not total rocket science here. It's just, if I could look one state ahead, that's denoted S prime, and then perform the most rewarding action for that particular state, denoted A prime. And now I just say, well, what's the expected reward that I just got plus the discounted reward I expect after that. That shouldn't be too surprising. That gives us this nice equation that's going to be satisfied for an optimal Q value, okay, Q star. Okay, so the point of the Bellman equation is you can directly use it as an iterative update formula in the vein of the iterative update formulas I showed you for V values. That was actually described via temporal difference before. But the Bellman equation is satisfied because all these things are very iterative, for one. So that's where it comes from, just kind of iterating one step of the definition of a Q value. And what they give us is an iterative update formula that I can use online as my reinforcement learning agent is, is doing self-play or doing some simulation. Okay. So there's the Bellman equation, and it basically follows that if I kind of iterate this enough in the limit of infinity, I get this kind of optimal guy, Q star. Okay, so let me show you the iterative formula in just a second. But as I've stated before, again, in any interesting problem, just about in AI, unfortunately, right? The size of the states and action pairs, for that matter, is going to be just colossal, right? So I can't store all those things as a lookup table. So I can't just use an iterative formula over and over and over again via a lookup table. What I have to do is perform some sort of compression, okay? And that compression can be done using, some sort of a function approximation. So we want to approximate, just to make that clear, we want to approximate the Q values, that is all the state action pairs for the optimal policy, okay? So one way you could do that is you could use a deep neural network. And if you use a deep neural network to approximate the Q values, the state action pairs, then you have folks deep Q learning, and that's exactly what the Atari DeepMind paper does. So just think of reinforcement learning, and then you append that with essentially deep neural networks. Technically, they're going to be deep convolutional networks because they're dealing with, I'll talk about that a little bit later in the next lecture. They talk about, or they're using image data, of course. But point is, we're going to approximate these state action pairs using a deep neural network. Because what is a neural network? If you're not that familiar with it, it's fine. But what is a neural network? It's nothing other than a glorified function approximator. Okay, so it's perfect in some ways. If we set it up in a smart way, it's basically perfect to perform this task. Okay, so there we go. Awesome. So let me just show you, I'm just going to jump ahead for 1 second. I'm just going to show you the formula itself, right? So I just want to get to this right here, yes. Okay, so how do you do Q learning in practice? So Q learning, again, these Q values satisfy these Bellman equations. By the way, there are a set of Bellman equations for the state values, the V of S's as well, but I'm just going to focus right here in the interest of time on Q values. So how could I learn Q values in practice? Well, you could initialize them all to 0 or something like that. You start with some state and then you repeat forever. As people like to say in reinforcement learning research and literature, the life of an agent is a trajectory. So in other words, it's a trajectory of a bunch of actions, rewards, over and over and over again. So I could start off with the Q values, set them all to 0. Say if I had a table, just in theory, initialize some state that I start with, repeat forever, take an action, get a reward, observe a new state, update the Q value, rinse and repeat, rinse and repeat, rinse and repeat. Okay, so what did I slip in right here? So this is, believe it or not, actually just taking the optimal Bellman equation and turning it into an iterative update formula. And this should remind you of the temporal difference kind of formula we had before, but now it's for Q values. So what does this say in essence? It says the Q value for the state action pair SA, the update is going to be, well, it's the previous value plus some eta, that's like a learning rate, okay, is usually a relatively small number, times what, this is exactly what essentially the Bellman equation had before, plus the reward I'm going to get when I'm in state S and I take action A, plus what, gamma, the discount factor, times the maximum action I could take in the next state minus the Q value of the current state action pair. So this is perfectly analogous, I hope that made sense, but perfectly analogous to the temporal difference formula I showed you basically, right? And it's, as I said at that point when I talked about that, it's, if you've seen these kinds of things, it's very much like the perceptron learning algorithm for weight update. So what this does is it pulls the Q value for state action pair SA closer to, right, the difference of these guys, right? So it's going to geometrically kind of pull it closer to, it's going to correlate these values to closer to that next state action pair, okay? And if I do this for many, many states and many epochs, right, and I, essentially search lots of different states and do, my exploration and my exploitation, right? If I sort of balance those things correctly, I should, in essence, get a good approximation for, many, let's say, of the state action pairs in the environment. Okay. So if you didn't do it this way, I could just think of replacing this update with a neural network or some sort of function approximator. People used to use regression models, linear models, by the way, even just before the Atari paper came out. That's part of the reason it was kind of a landmark paper. But you could approximate these things with like just a big linear model in essence, okay? Didn't give you as good results, but nonetheless you could do that, okay? So if I have these Q values, here's an update formula that I can do on policy, right? Or sorry, not on policy, but on online rather, as we're performing simulations itself. Okay, so there's a lot of little caveats and little nuances that I'm kind of brushing over again, just so we can get some exposure to reinforcement learning, just so we kind of know the big picture stuff right here at least. So one question is like, okay, wait a second. If we go back to this kind of repeat forever sequence. So I take an action, I observe a new state. How do I take this action? Like, what am I basing this on, right? So there's kind of two general approaches, right? I could base it on the policy I'm currently learning, and that would be what's called on policy learning. So if I'm doing these updates to the Q values all the while I'm playing the chess game or I'm doing this simulation, I could base if we go back to here, I could base my next action on those Q values. As I told you before, the Q values themselves, right, give you a policy, right? They lend themselves, or they kind of inform a policy in an intuitive way. So I could use the current Q values as I'm updating them to take actions, and that would be called on policy. Or on the other hand, I could scrap that, and I could just maybe, for instance, just to make it simple, choose these actions at random, or use a different policy, not the one I'm learning, in fact, and that would be called off policy learning, as you might imagine. Okay, pros and cons and different strategies in both places, as you might imagine as well. It's very deep, it's a very deep domain, but there's sort of two general approaches. Okay. So point being, just to summarize that, we want these Q values. The Bellman equations give us an update formula that we can do online. We can do as we learn. Now the question is how you actually perform life as a trajectory in reinforcement learning. Again, there's the old adage. How do you actually choose these actions while I'm doing my simulations? I could choose them based on the policy I'm learning. That's called on policy. Or using a different policy or random policy altogether. That would be called off policy learning. Okay. So, and then when I choose the actions, of course, I probably don't want to be super greedy, because then it's going to be too much exploitation, right? I want to make things a little bit maybe stochastic. Epsilon greedy would be a way to choose actions as well. So usually I don't just follow policy, but I follow an epsilon greedy version of the policy for Q learning. Okay, and we've talked about epsilon greedy before. So let me just show you with a simple example here how, again, Q learning is not a horrendous thing. And in fact, pretty easy to implement for the most part. So if we consider, again, a very elementary example, A is our agent who takes an action at each time step. Only action in square one is to move forward. So basically you can move forward or backward from any of the other squares. And you want to get to square 4 because you get $5 or whatever the case may be. So there's the reward. The only action in square 4 is stop. That's the end of that episode, as it's called usually in reinforcement learning. And there's no other rewards or penalties otherwise. And then let's say the discount factor is 0.9. So again, there's some urgency to get to 4 as fast as possible. And we'll say the learning rate 8 is 1, just to make the math kind of simple. Okay. So how does this go? If we just follow my kind of recipe I had a couple slides before, there we go. This is the iterative formula I'm going to use to update the Q values, the state action pair approximations, as I run my agent. And let's say we initialize everything to 0 on some level. Okay, so let's start with everything at 0. And we're in state 1. Current state is 1. Okay, cool. So we can only go forward. So let's go forward. Again, here's our simulation. And as we're simulating this episode of this very simple game, we're going to update the Q values. Okay, so we move to state 2. So our reward is 0, and now we're in state 2. Cool. So now we go to the update formula. It's very simple. And we're looking at the reward we just got, which is 0. What's the max of the actions I can take from state 2? Well, just looking at the Q values, right? They're all 0. So nothing to update there. It's still going to be 0. Okay. So again, we're episode 1, first time playing the game, as it were. We're in current state as S2. We could go forward or backward. How about we query forward? Let's try that. So move forward. Cool. And now we look at the reward. We got 0. We're in state 3. We look at the update formula, iterative update formula. So here's the reward we just got. The discount factor is 0.9, and then the next, the next state of the next states we could look at would be 4 or 2 in that case. Okay, and then we move, and there was nothing to update there. It was all zeros, and then we move forward again, and now finally we get a reward of, let's say, 5. We're in state 4. Now we update the Q value in that case. So the Q value at state 3, right, looking forward now, the reward we're going to get is, so this is saying what's the Q value of being in state 3 and performing action forward, right? That should have a non-zero Q value, because that's a good thing to do when I'm in state 3, obviously, right? So here is the, just to remind you, the current Q value for state 3 moving forward. If I just look at the chart, it's a 0 there, plus the reward I just got and the discount factor. And then we look at the difference between the next states and actions minus the current value. So that's going to be 5. There are no other states, other actions I can take. Remember, we stopped there. But importantly, we did get an update to that state action pair. Okay, so what is this saying, just fundamentally, just to make it intuitive? This is saying when you're in state 3, going forward, right, is highly desirable, of course, because we're one step away from, winning the game, as it were. Okay, so there's maybe and then state 4 we stop. And there's kind of the end of episode 1. Okay, that's one simulation. Obviously didn't have a profound impact on our Q values, our Q table. But nonetheless, it did update this one. But now there will be this kind of cascading effect, right? Now when I go back and let's run through again in episode 2 and walk through, one more simulation of this game, that should now propagate this 5 value to other states that should be desirable. As you could imagine, state 3 should be more desirable, or state 2, right, coupled with forward should be more desirable than 0 or going left, right? So we should get some of those updates that start to cascade in the second and third episode. Let's see how that goes. Again, all we're doing the whole time is just thank goodness for the Bellman equations, because they give us this fantastic little update formula that we just keep running. Very simple, right? Okay, so we're in episode 2. There we go. We move forward. Awesome. So now we're in no reward, state 2. Still going to be 0 now. Current state is 2. Let's say we go forward. Okay, then we're in state 3. That's S prime. And that's the little look ahead. This is where I said now it's going to trickle down to some of the other Q values in the table. So if we look at the update formula, so the current value was 0, the reward was 0, discounted, but now we're sort of pulling the fact that the next state is desirable, right? That's going to have some influence on the Q value for the current state if I move forward. And so punching in those numbers, you can check all that. We get 4.5. So notice that got updated. This should make a lot of intuitive sense. When I'm in state 2, the thing to do in this, again, very simple game is to go forward. I don't want to go back, right? So it's to go forward and, and that certainly it got rewarded, right, in terms of the Q value accordingly. Okay. Cool, and then we're in state 3 and we go forward and we can do an update here. We get reward 4, and then that's not going to change in terms of the math, but we do run it through the iterative update formula. It's still going to be 5. It's kind of the maximum value could be. Okay, so we're done with episode 2. Life is a trajectory. It's a game, right? We keep playing it to get better and better approximations for our Q values. So episode 3 now, current state is 1, move forward, cool. We get no reward. State 2, we do an update, okay? But now, again, the cascading effect is really happening now, because now we're going to get an update to that state action pair. So now when I'm even in state 1, even though it's a couple steps removed from the goal, it still says going forward is the thing to do. Okay, so we get that. Now let's say we go to state 2 and we go back. Okay, don't just go forward the whole time, of course, right? We want to do this would be like an off policy simulation. It's not doing the optimal thing, it's doing a suboptimal thing, so we get an exploration step. So we go back to state 1 would be our S prime, no reward, of course, and we get an update. And so the update formula, again, just punching in those numbers, is the Q value for 2 going back is going to be, notice it's not 0 or negative necessarily, but it's 3.65. But this is telltale, right? This is saying when I'm in, at this point, if we freeze things, when I'm in state 2, and I want to say, do I go forward or backward? Well, according to the Q values in the table, it's much more desirable to go forward, right? Higher Q value, and that should be intuitive. Okay, episode 3 can go forward again, then we're in state 2, do an update, etc., etc. I think you get the idea from there. Okay, guys, I'm going to end this lecture here. I have some more information if you're curious about backgammon, TD gammon. So TD stands for temporal difference. So this was developed in the late 80s. You're welcome to check this out. It's a very cool idea. I think I prefer just to bring things up to speed to talk about in more depth the Atari DeepMind paper, because that's kind of more in line with the deep learning flavor of things today. But absolutely, you should check this out. Check out these slides. It walks through how TD backgammon, this was a major result that predated, of course, Deep Blue, AlphaGo, etc. And it was one of the first computer programs to actually beat, I think it was one of the best players. I don't know if it was the number 1 in the world, but one of the best players at backgammon in 1989. Just using reinforcement learning, using actually the temporal difference formula I basically showed you a couple slides back. And it's not a trivial problem. I just want to state that too if you do decide to check this out. So the number of possible states is like 10 to the 20th. That's a very large, especially in 1989. You could not exhaustively search that. There are lots of different, it's a stochastic game because there's dice combinations and stuff. There's a large branching factor as well. So it's a complex game, but basically that was considered essentially solved, and there's been various updates to it as well. So I do encourage you to check that out. And then I will upload this, and we'll also have the DeepMind Atari paper to check out as well.